Hey everyone, just a few quick words before we get into the interview with Chirru and Vivas. When I originally booked the interview, I booked it for an hour. Now what I quickly found as we got into the discussion is that both Chirru and Vivas have a lot of information locked away in their brains, and it could have easily have been an hour discussion with each one of them because they're both very engaging. Now, I also tend to look at companies from as many angles as I can, from the strategic down to the granular. That means we covered a lot of ground in 1 hour. And for the viewer, that can leave you chasing the interview a bit, or chasing the discussion a bit. So what I'm going to do throughout the video is I'm going to drop in from the editing room and just give some insights as to what's being said. So with that out of the way, let's kick into the video. Welcome back, everyone. I'm Jordan Giesecke, and this is The Limiting Factor. Today, we're going to be speaking with Vivas Kumar and Chirranjeevi Gopal from Mitra Chem. Now, Mitra Chem hit my radar late last year because they're intending to manufacture battery-active materials here in the United States. Now, that's important because something like 80 to 90% of the material supply chain, the battery material supply chain, goes through China. Another thing that interested me about Mitra Chem is that they're intending to reduce the time to market for these battery materials by 90%. Now, as far as I'm aware, that's about the extent of what's publicly available on Mitra Chem. So I invited the team today to have a discussion so I can pick their brains a bit more and learn about what they're doing. So with that, let's kick into the interview. Guys, thanks for making the time. I appreciate you coming along to share what you're doing.
Thank you, Jordan. It's a huge honor for us also, given that you run one of the premier battery channels, to be invited to your channel today.
Thanks. Now, it's probably a good place to kick off is just a little about what your backgrounds are.
I am an immigrant to the US. I was born in India and grew up in Singapore. And I've been in the States for my education and most of my career now. Most recently, before Mitra Chem, I began my foray in batteries when I was one of the senior managers managing the battery supply chain over at Tesla. So I was responsible for sourcing multiple of the materials that ultimately went into the Reno Gigafactory. And I had a wonderful experience doing that and decided to take a break to get educated at Stanford University. And simultaneously, while doing that, was a principal at Benchmark Mineral Intelligence, which is one of the premier consultancies and market research firms focused on the battery supply chain globally. And through my affiliation at Stanford is where I met my two co-founders, Will Chu, and of course, Chirru Gopal, who's here with us today. And we got together and started Mitra Chem.
Sure. What's your background?
Yeah, this is interesting. I'm pretty sure Vivas and I were born within 3 miles of each other in southern India and Chennai, and then eventually got together in Silicon Valley, as you do. So I was born in India as well. I immigrated to the United States in 2009 to start my PhD at Caltech. So I'm a physicist, a material scientist by training. Spent about 7 years in academia doing research on oxides for fuel cells, batteries, basically all sorts of energy conversion and storage devices. And I've spent about 6 years in the industry since then, developing machine learning and software tools to help accelerate experimentation, right? Whether that's in genomics, learning from the genomics field where this sort of informatics revolution has already taken foot. And then prior to Mitra, I did something very similar at Toyota Research, where I was developing physics-informed machine learning models to help accelerate both battery testing and shorten testing times, and then helping optimize battery development over large dimensional spaces. So any problem, if you set foot in battery development, is typically involves a lot of related factors. So how do you find the winning candidate amongst thousands of possible things that you could do, right? And that eventually led me to meeting my co-founders, Vivas and Will Chu, with whom I co-founded Mitra. So I would say I'm a material scientist by training and a data scientist by practice.
That's excellent. You have background in real world applications. You've been working in industries, and in particular, accelerating the speed that we can develop battery materials. It's a particular interest for me, but something I never had a chance much to delve into except for the first few videos I did for the channel. So it's probably good lead in to kick off and look into what the genesis of Mitra Chem is and what problem you're trying to solve there.
The ideas that underlie the founding of Mitra Chem for me began in my time at Tesla. As a matter of fact, there's one conversation I can pinpoint that my team had with Elon back in 2016 that led to us thinking about the ideas that ultimately became Mitra Chem. So back in 2016, Elon was saying to us, look, today we have the Model S and X, which are both, for lack of a better way of saying it, luxury vehicles. But 5 years from now, we're going to have multiple different products in multiple different segments in automotive and in energy storage. Today, we use NCA chemistry, but in the future, we want to have a diversified cathode approach, which is the exact wording that they said during their battery day back in 2019. And so if we're going to have a diversified battery approach or a diversified cathode approach, we want to move batteries to be a platform technology for energy storage rather than a powertrain for vehicles. So in the same way that semiconductors are a platform for computing and informatics, batteries will be a platform for energy storage. But in order to do that, we need to be able to differentiate how a battery performs according to customer-driven specifications. And so we as in the team, went out and had conversations with all the major cathode suppliers, all the major battery material suppliers. And we found that their limiting factor to bring new products to market was the time needed, and the speed was quite slow for innovating on battery materials. Now, the reason for this is Chirru can talk about what is called the design, build, test cycle.
Sure. Yeah, so there was actually an article out very recently on Wall Street Journal, which sort of spoke about how breakthroughs in batteries are often taking so long that even incremental improvements end up catching up by the time a breakthrough comes, which is typically every decade or so, right? I think it came out a couple of days ago, actually. And the fundamental reason for this, Jordan, is that at the end of the day, if you want to make a better battery material and put that into a battery and make the battery better, there is no substitute to actually doing the actual experiment yourself. Meaning you have to take lithium carbonate, iron phosphate, or sulfates of nickel and cobalt, mix them together, fire them in a furnace and make a cathode, put it in a cell and test it, right? This process, ultimately what the customer wants is how does the powder behave in a cell? It's not about the shape of the particle. It's not about what the density is, right? This process, going from taking raw materials to getting cell level data, can take anywhere from 12 to 18 months, right? That is for you to be able to ask, hey, I made this small change. How long do I have to wait to get data out, right? That's a really long time to wait. And now if you have to do 10,000 of these experiments to find something that works, this is a really long process. So talking about what it is that Mitra Chem is doing to expedite this process, two principal things, right? Run each experiment short, make each experiment short, meaning how do we use models to help shorten this testing timeline from 18 months down to a month, possibly, right? So giving you a 10x improvement in speed, but also how do we only run the experiments that matter? We know that we have to run the experiment. So how do we only run the experiments that matter? So how do we learn from the successes and the failures of the past to inform the next set of experiments? It's known as active learning or Bayesian optimization in the machine learning and data science world. But how do we basically take these concepts, which are taking a foot in other fields, and use it to power battery materials development? It is a very difficult problem, and it's a very challenging one to do this in a real world application. But these are the two core differentiators that Mitra Chem is bringing to being able to accelerate a new product development and put it in a mass market EV.
So there are two things that can be easily confused here. First, materials development can occur at a fundamental level, which is developing a material for the first time. And second, materials development can occur at more of an industrial level, which is the process of refining the specs of a chemistry for a commercial product. Chirru is talking about the latter here, and that's really significant and important because that's where the rubber hits the road. That's what enables cathode materials to be mass-produced for products. For example, at some point, somebody decides to mass produce oatmeal cookies. Now, what they have to do is they have to develop a recipe that's fit for an industrial process where they can just crank out these cookies and they look the same every time. So they have the correct amount of shelf life. And even so, they can just amend the recipe to suit different markets. And that's what Mitra Chem is looking to do. They're looking to accelerate the speed that new recipes can be created that are useful for an industrial process. Now, what Chirru is saying here is it takes roughly 18 months to test a new recipe. And what they're looking to do is to reduce that to 1 to 2 months. Now, in order to create a new cathode recipe, you actually have to do thousands of these test recipes. So what you can do is you can run hundreds of those tests in parallel, and each of those tests taking 1 to 2 months each. You can create a new recipe in about 6 to 12 months. And that's much better than the typical, where it takes 12 to 18 months for each test recipe, and then something like 5 years before you've run those thousands of tests and you actually have a viable new recipe. This is important because different cathode manufacturers, even if they're producing the same cathode material like LFP, they'll have different raw material inputs with different characteristics. And they'll also have different customers with different customer requirements. And all of that necessitates different recipes for different situations. Furthermore, they also have to deal with a constantly evolving market. So the ability to rapidly iterate on the recipes you can use as a cathode manufacturer, the better position it puts you in competitively. And this is something we know. Elon Musk has said several times that your pace of innovation is what determines your success in a competitive market.
I was curious as to whether the market is moving towards like a single chemistry or a more differentiated approach. And what you're saying is that we are going to need multiple different types of cathodes for different applications. And what you're doing is you're accelerating the speed that you can differentiate and selecting the right material more quickly.
Basically, what I'm looking for Chirru to confirm here is what we've already discussed, which is that Mitra Chem has the ability to rapidly iterate on cathode chemistries. And one thing I was trying to drive at here, but I didn't articulate it very well, is that there's two potential positive impacts of that. One is that you can more fully and more completely use your existing material supply chains. So you don't have to switch to a new chemistry. You can hold off on waiting for a breakthrough and more fully utilize what you already have. But there's also interesting implications for the future, which is that Mitra Chem should be able to develop entirely new chemistries much more quickly than we were able to do in the past.
Yes, exactly. Yeah, that's right.
All right.
Yeah. Mm-hmm.
And we coupled that, Jordan, by being a product company, where everything that we're describing around the acceleration capability that we bring to R&D and new product development is an in-house advantage that ultimately gets us to making products. The tight coupling of this physics-informed machine learning layer that we're building on top of the experimentation that we're doing that goes from synthesizing powders all the way to cell building in-house is only good if we actually produce cathode powders at scale that can be used within the battery supply chain here in North America.
Mm-hmm. I want to be clear on what your scope is. So you're saying that you're going to be going from developing the raw materials all the way to manufacturing the cathode powder, or are you also getting into cell manufacturing? I guess what place in the supply chain are you looking to fill?
I think our business model is going to be commercial production of cathodes, right? So we are going to be innovating on ion-rich cathodes and mass producing them. That is how Mitra Chem. That's how Mitra Chem is going to go to market, right? The aspect about infrastructure and the acceleration I spoke about is how are we going to do that faster than what has typically been done, right? And to answer your question about cell manufacturing versus cathode manufacturing, right? It's important to do one thing really well in this business and do that at scale. Right, cathode production, specialty chemical production. The material qualification timelines are already long as is, and it's important for us to get that right before even thinking about going into cell production. Right. So our belief is that whether we end up selling cathodes to cell makers or directly to OEMs, that's a different thing. Our goal is to stop at cathode production.
But Jordan, we did talk about cell making, and the reason is because the cell is a system of which cathode is one component. Simply producing cathode powder is not enough to generate confidence within the large cell makers and automakers that our product can qualify. So there's a commercial reality, which is if you were to bring the best specification, the best technical product to market, you still need to qualify that product for it to be used at a large scale at an auto OEM. And they're going to require you to prove within their cell that your product can be a drop-in solution that hits the specifications that they require. So that's why cell construction and testing is part of our R&D workflow, even though we intend to be a cathode active material manufacturer.
So do you have to be able to produce the battery cell in the format that they're using? For instance, if they're using prismatic, if they're doing pouch, or if they're using a 4680, do you have to be able to produce a 4680 battery cell? Or is it just in general, you have to be able to prove that it works at the cell level?
I think it's somewhere in between, in the sense that we can't be just doing things in a coin cell, right? But we also are a material supplier. The goal is to qualify our materials at a scale that's relevant, meaning that we pick one type of cell format, which is commercially relevant, say the pouch cell, for example, and do it at an electrode area and a capacity of the cell that would deem the process as being scalable. Whether we can do, if we can do roll-to-roll coating with the electrode and show that our cells work at a 50 centimeter square electrode area, for example, then whether we do it as a prismatic or a pouch cell is less consequential than, importantly, showing that we can make a certain amperage hour cell in-house.
Jordan, think about how much innovation there's been in form factor recently. We had a paradigm where it was coin, pouch, prismatic, and basic cylindrical for a while. Then it was 18650s, then it was 2170s, and then now it's 4680s alongside blade, which is a whole new innovation. Form factors will continue to evolve as customer definition around the right form factor for the overall pack and energy storage and discharge characteristics will continue to evolve. What we need to do is to be able to keep up with them. And that's why R&D acceleration is so important to us as an in-house advantage.
Yeah, there's like a Cambrian explosion going on with battery materials and battery form factors. It seems like the market's going 10 different directions at once.
Yep.
Now, let's start getting into your process as to what the typical process is for battery development and what you're doing to accelerate that process. Because you've spoken about AI, but I'm also curious about automated potential building and testing of cells, besides using AI to pick what materials go into those cells. So could you walk me through what you're doing?
Sure. So the acceleration that we talk about comes from sort of four distinct advantages that we like to think about, right? So conventional R&D process to go from taking raw materials that go into becoming cathodes, putting them in a cell is a very linear process. You mix the materials, you fire them. When you've made a cathode, you put them under a microscope or some sort of a measurement instrument and understand, hey, how is my powder doing, right? You measure those performance metrics at the powder level, tap density, crystallinity, phase purity, and all that. Then you put it in a cell, test a cell. What we believe is important is to have a workflow where at each step you have checkpoints to be able to call off. The number of possibilities is huge, so you would be wasting a lot of time if you ran every experiment to the end, right? So how do we develop workflows which accelerate every step of the way? And call off bad samples along the way. The next step is basically how do we, a key bottleneck is testing. And we already have some experience in applying machine learning methods to accelerate testing, right? Which is, how do I only use 100 cycles of data to call off something that happens at the end of 1,000 cycles? Yes, we might not be entirely accurate, but from a screening purpose, that's enough, right? Living with uncertainty is okay, so long as you're only screening. Of course, when we have to give a powder to a customer, we are obviously going to test the samples until the very end. But from internal screening perspective, that's okay. So using these testing methods to accelerate every experiment, running only the most informative experiments, and combining that basically with, as you mentioned, automated data acquisition wherever possible. Like one of the most slow steps is actually making physically the cathodes, right? So how do we achieve more throughput per operator? By combining the latest instrumentation with automated data extraction pipelines. Ultimately, it comes down to how do you enable decision-making with data? And a lot of that comes down to making sense of data from synthesis, all of the sensors which monitor these processes. A human can only do so much. So the moment you start using data infrastructure in-house to be able to make sense of all of these diverse data we're getting, we increase the throughput per operator. Ultimately, one single metric that we like to think about that matters is how much dollar spend you have per R&D variation, right? That is time, that is personnel cost. All of these can bake into one simple thing. If you have X amount of dollars, how do you best spend that in terms of developing and building a product? And that's what we're going for.
Now, I've seen two different theories as to how you accelerate the development of something. I've heard people promote the idea that you have like as big a team as possible and you just brute force it. And other people who say, all right, it's better to work in a smaller team and then use those learnings as efficiently as possible to move forward. So could you give your perspective on that?
I think basically that's a great question, right? So if I ran every experiment sequentially, that is the most efficient use of resources, but it'll take you a long time to get to a successful product, right? If I had $1 billion in my war chest, I would care a little less about putting 10,000 channels of cyclers in my lab and being able to do like a shotgun approach, basically, right, to getting a new product. So dialing that somewhere in between is the right trade-off between resource utilization and time, right? And this is what I mentioned, that you can't run all experiments at once because that's a complete waste. So how do we basically you need a critical mass. In this field, it's known, right? Making battery materials and testing them is going to take some CapEx and some operational expenses. But the question then becomes, how do you get better at it as you progress in time? So initially we'll do have some baseline, but as we do it, it's like a flywheel effect. We get better and better over time.
That's super helpful because it seems like there's so many situations where people go to one extreme or the other and choose that as like the optimum, but usually the truth is somewhere in between. So that's given me some new perspective and a bit more balance on the push and pull between those two.
Mm-hmm.
Now, my understanding is you're focusing on lithium iron phosphate chemistries. Is it just iron chemistries in general, or is it specifically lithium iron phosphate?
So we are starting with lithium iron phosphate based chemistry. And what I mean is, our goal is to go beyond LFP, lithium iron phosphate. And the way to do that is to fundamentally modify LFP in terms of coatings and dopings and all of that. But the point is we have to start with a chemistry for which the manufacturing processes are known to be scalable, so that when we develop a product off this, our path to scale up is going to be a lot faster. And this is the reason for why we are choosing to start with LFP, lithium iron phosphate. But the goal eventually is to be able to innovate in the long run, an iron-rich chemistry that doesn't necessarily exist in the market today, but one that's desperately needed.
So earlier we mentioned that there's a couple of different innovation approaches, right? One is you come up with a battery breakthrough from day one, or the second is you compound incremental gains over time such that you get to a better volumetric energy density, gravimetric energy density, lifetime, voltage curve, cost, whatever metric you want to measure in the dance of optimization that is, battery chemistry and battery performance. The reason that we've chosen the approach of compounding incremental gains is beyond the fact that it is technically possible and fits within our ethos of R&D acceleration. It also reflects the commercial reality. If you start with a known chemistry that is already industry accepted, your material will be accepted for use faster. Your company will be able to generate cash flow faster. You will be able to work with the downstream players in a much more strategic way to bring the future products to market themselves. So initially, there was a bit of a head scratching when we were telling people, look, we really love LFP. And I don't need to tell you, Jordan, this because you have an amazing series on LFP where you explain exactly why LFP is a great chemistry. But as we've seen now, the Western market has started to shift towards accepting more and more LFP for mass market solutions. There's questions around this 4680 from Tesla also incorporate LFP. Of course, Blade is starting to make a lot of noise within Western mass market EV solutions. And we think that this chemistry has been a dark horse for a long time, but it is here to stay. And their innovation space within the realm of iron-based cathodes is massive. That's why we're excited to work on it.
All right. There's a few things that you mentioned there that get deeper into the future, but I'm really excited about. So probably the first thing is when you're talking about the innovation space for LFP, one thing that I haven't researched LFMP yet, or LMFP. I'm not sure what the correct order is, but when you're like generating that LFP crystal, can you just trade some of those iron atoms for manganese? Is it sort of infinitely variable? Could you do, like, for instance, 70% lithium manganese phosphate and 30% iron, or 70% lithium iron phosphate and 30% lithium manganese phosphate? What are the options available there?
So the answer is it depends. And sorry for giving a very legal sounding answer, but it depends on the type of the element, right? So whether it's vanadium or manganese or cobalt, the amount that you can swap out will change, right? The second is also the process aspect. At what step you mix manganese and iron also dictates how much you can swap them out interchangeably for. Things mix really well in liquid phase. So when you make the precursor stage, at the precursor stage, you are able to achieve a much greater degree of substitution mixing than is possible if you were to just physically mix powders, right? Ultimately, thermodynamics dictates what you can achieve in terms of a limitation, right? So because manganese and iron are somewhat similar in terms of their chemistry, it's a little easier to swap the two, essentially. So the mixing is, I would say, over a much larger range than is possible with other chemistries, for example. But that being said, it doesn't necessarily translate to performance in a similar. So performance is not necessarily a linear combination either, because it leads to a lot of differing degradation behavior downstream.
Okay, so on that note, what are the positives and negatives of adding some extra manganese to lithium iron phosphate?
The most obvious benefit that manganese affords you is the fact that the redox voltage is higher, right? So just by swapping some proportion of manganese, some iron out for manganese, you get that much of a bump in the energy density. The capacity is very similar. The energy density becomes higher because you're multiplying by the voltage, right? So that's an obvious pro. The con comes from the fact that now all of a sudden you have not very uniform sites, like iron and manganese is slightly different. So the transportation pathways become a little bit more mixed, and you take a small penalty in transport. And there are other performance degradation issues specifically around manganese and coatings. That is also a drawback which has kept LMFP from being in commercial cells today. But I know there's a lot of companies that are actively working on it at both at a cell level and a pack level.
So when you're referring to transport, are you referring to the speed that the lithium exits and enters the crystal?
It's electronic transport.
Okay.
And lithium, both ionic and electronic transport. But specifically, one of the issues with LFP is it's a one-dimensional transport system. So when you make LFP, the ability for lithium and iron to sit on each other's side often can hinder the ability to achieve good electronic connectivity. Adding manganese can help, but anytime you add another element, the properties do evolve. And you do take a small penalty in the electronic transport as well when with LMFP.
Okay, and then what would be the impact of that for the final cell? Would that affect the speed?
The rate capability, yeah, exactly. The rate capability you can achieve, polarization resistances, and all of that. And you could also accelerate side reactions because all of a sudden this resistance causes you to have other side reactions, which can be favorable pathways for conduction, for example.
Okay. And I'm getting a little bit deeper here, but I think it's important for people to understand like all the variables that are involved in making a battery cell. So say, for instance, if you did use like an LMFP chemistry, and would that also increase the amount of heat that's generated for like a specific volume or specific weight of material? Or would it just affect the rate?
So from a thermal runaway perspective, it would depend significantly on how you use the cell as well, right? Mm-hmm. So LFP has fairly high temperature resistance. Adding manganese to it will affect the onset temperature for thermal runaway. The exact temperature, once again, depends upon the use case conditions.
When a customer purchases their vehicle, right, they are not thinking about all of the millions of decisions that have gone from thousands of engineers like this conversation that we're having. They just care that it works. So I love that we're having this conversation because hopefully it lifts the hood, no pun intended, to show just how many micro decisions go into making that optimized battery cell to power your vehicle.
Precisely. And that's exactly what I was trying to do, is just lift the hood a little bit so people go, oh, wow, there's like, and we could go on this like this for hours having these discussions. And that's probably what you do spend a lot of your time doing, is just going, all right, these, you know, are we thinking of all the trade-off decisions? And you might even have a model for that or some decision-making process, but regardless, these conversations need to be had because these things affect the form factor. They affect how thick you're going to make the cathode and anode, et cetera. It's just, you know, you change one thing in a complex system and it has a ripple effect throughout the entire thing. Yep. So constant discussion to get it right. Now, I just have to regain my train of thought.
Sure.
Yes.
I'm going to bring you back to, you mentioned a couple times, the incremental approach versus the breakthrough approach to moving batteries forward. One thing I've been researching is sodium ion. And I'm like, all right, well, sodium ion has some first principles advantages, but lithium iron phosphate is constantly improving. So to me, it's an interesting case study. Which one of these is going to succeed? It seems like sodium ion might succeed in the long term and start displacing some of LFP, but how long is that going to take if LFP is continually improving? Now, I know you don't have the answer to that question, but is sodium ion something that you've considered, and how do you view that as competition to LFP?
I will be honest. So I am aware of the sodium ion chemistries at a high level, but I don't understand it to the same extent as we do with LFP. But the reason that we are taking a bet on lithium ion and LFP specifically right now is exactly the reason what Vivas mentioned in terms of that is a huge market need right now for a low cost cathode, specifically ion-based. And our solution to this is to pick a chemistry whose operations are very well known and be able to innovate on the chemistry and the scale to be able to bring a product to market fast, right? Having done that, then, as I mentioned, there is much wider opportunity in terms of innovating on ion-rich chemistries that are not existing. We often mention ion-rich chemistries. We don't necessarily say lithium ion-rich chemistry, right? So which route we go, I think the road is wide open over there. But I think in the short term, at least, we definitely feel that it's that lithium ion chemistries are here to stay and LFP is here to stay for a while.
Oh, yeah, and absolutely. That's one thing that I think people don't appreciate is there's companies that have invested a certain amount of or quite a bit of capital in their existing machinery. And you can't just flip from an LFP chemistry to a sodium ion chemistry. So even if something like that does come in the future, there's a demand right now, and there will be demand for years for improvements in LFP to optimize the current equipment they have. And that's not even taking into account the entire supply chain that backs all that up.
Yeah, so the reality of scale up and the reality of innovation at the R&D level are two very different things. The difficulty of scale up cannot be underestimated. Now, let's be very clear. Mitra Chem is not scaling up to a 100,000 ton per year facility right now, although it's our aspiration to do so. And it requires a completely different skill set than what we have today in the United States. There is no large-scale industrialized cathode capacity in the US yet. Now, something else I want to say about this is that doesn't discount the importance of thinking about scale-up from R&D. Decisions that you make at the 1 kilogram scale do propagate all the way to the 100,000 ton scale, if you want to talk about that, Chirru.
The question you bring about what's beyond and what we think about the chemistries beyond is an important one, right? And this is why while we are prioritizing, while we are a product company, we are prioritizing the infrastructure on an even keel. Because at the end of the day, there's a very high likelihood that a lot of the strategies that we are thinking as viable could be a dead end. And it often does happen that, the first 2-3 ideas you try in battery materials companies do not work and you have to pivot. And our whole thesis here is that battery materials optimization is fundamentally a big space. And I think setting up an infrastructure which allows us to have a rapid timeline to go from concept to a product in the market is going to be beneficial, whether we choose to run LFP or beyond, basically. Now, to bring back to what Vivas said around the relevance of scale, one thing that we are emphasizing on, aside from this R&D acceleration, is what we're calling as like a scale-up translator, right? And what we mean by this is the conventional approach is let's develop an idea at a few gram scale, find a cathode that works. Then I'll put it in a muffle furnace, test it at 100 gram capacity. And then when I've qualified in a cell, I'll then go into pre-piloting or piloting, right? What we are trying to do differently as well is to bring everything from an R&D to a pre-pilot scale in-house. What I mean by pre-pilot, useful to think about mass batch sizes, right? A typical R&D size is anywhere from 10 to 100 grams. Pre-pilot, you can think of it as one modular unit of like a multi-line unit you will see in a pilot scale calcination facility, right? You have a roller hearth kiln that makes your cathodes. We are buying one of those like simulator units to have in-house. Why? Because the moment we have a candidate that looks promising at R&D scale, pop it in the larger scale oven so that when we can talk to a customer and say, hey, we have proof of concept, we are talking about tens of kilograms, not just hundreds of grams that is typically done at an R&D scale, right? And which is why it's all about down selection, but not just do serial down selection, have the down selection timelines or the funnels be somewhat overlapped, essentially. So as and when we have promising candidates at an R&D scale, we are basically testing their feasibility, process optimization at 2 orders of magnitude higher production batches as well.
Down selection is pretty straightforward. It just means working through a number of potential candidates to arrive at your final candidate. With regards to larger batch sizes, as batch size increases, it becomes more difficult to control the specs and the variance. Now that's important, of course, because as you're working towards commercial production, you need larger batch sizes. So larger batch sizes during their testing process means that Mitra Chem is better prepared when they sit down with potential customers. For example, going back to our oatmeal cookie analogy, let's say you want to sell a lot of cookies, and the best way to do that is to go to a store, meet with the store so they can stock their shelves with your cookies. If you show up with 10 misshapen cookies that were produced out of a home kitchen, they won't be terribly interested or terribly convinced by your conviction. But if you come and you meet with the store and you have 1,000 cookies and each one of those cookies is perfect and you're producing them out of a commercial kitchen, they know you mean business and they also know that you're prepared to stock their shelves, and makes that conversation a lot easier.
So just to re-encapsulate what you're saying is at the beginning was speed of innovation is what you're focused on. And regardless of which material path you choose, it's the people, the process, the way you go about these things that matters. Because regardless of whether you choose lithium iron phosphate or sodium, the key is to innovate quickly. And you can apply that process that you develop to different materials.
Can I give a quick flavor to that, Jordan?
Yeah.
It's not just the speed as well, speed at a relevant scale, right? And that's something that's often forgotten, right? So we could do this we could have like a microgrid of different samples that we could have an automated robot be able to synthesize samples for us and generate data. But the question is it at a relevant scale, right? So then that is important. And this is what we are trying to do, right? And the difficult part is how do you do high throughput fast, but also at a relevant scale? And these are the three things I would say are points of emphasis for our infrastructure.
So you started this like last year, I think it was. And
Yes.
how long do you
Yep.
think it's going to be before you're producing cathode commercially that goes into battery cells? And what are your plans for the company in the next few years?
Mhm.
So we started the company. We're recording this in March 2022. We started the company approximately a year ago. We capitalized the company approximately 9 months ago with our Series A financing. And the goal from that Series A was three things: build the first product, build our
Mhm.
team, and build the lab. So we know what our first product is: an iron-based cathode that can achieve a higher energy density than today's leading LFP solution through compounding incremental gains. Building the team, we are a team of a confluence of material science skills and data science skills, all within our lab here in Mountain View, California. The lab is capable of producing, by the middle of this year, 1 kilogram batches, and by the end of this year, that pre-pilot scale batch that Chirru was talking about. Now, ultimately, what we want to get to is pilot scale production that sits co-located alongside this lab here in Northern California by the end of next year. So that's 2023. To get to large scale production, so we're talking tens of thousands of tons for production per year in North America, at that point, we'll need to find a customer with whom to do it. So one of these automotive OEMs or cell manufacturers who is building up large scale battery cell capacity to be part of the EV and ESS revolution. Now, what we want to do is ideally co-locate our facility alongside their cell plant, because having a vertically integrated supply chain hub is the most efficient way that you can go through battery cell manufacturing. So we are open. We can go to anywhere in the United States or Canada for that large scale manufacturing. And that can happen within about 3 years after we've commissioned our pilot plant and gotten product qualified by the customer.
Now, do you have any concerns about sourcing materials? How
the concerns around sourcing materials is also something that pushed us towards LFP and iron rich rather than going ternary. If you look at the dislocation between demand and supply for the supply chain of nickel and cobalt chemicals, there is no way that all Western mass market automotive solutions and energy storage solutions can use the ternary cathodes that have been in vogue for the last 10 years in Western markets. So we wanted to shift away from ternary chemistries, which use 3 different materials: lithium chemicals, nickel chemicals, and cobalt chemicals, which are all facing imminent supply shortages, towards LFP with a more robust supply chain than exists, with a more robust supply chain. Now, there's 2 different ways that we need to think about this. I'll talk about lithium chemicals. Chirru can talk about the FP precursors and our make versus buy decision on that. So for lithium chemicals, this market is in severe shortage. Once again, we're recording this in March 2022. There has been a double-digit % increase in price for lithium chemicals every week this calendar year thus far already. Part of that is because we're just coming out of Chinese New Year, when generally speaking, inventory is reduced and production is reduced. And given that so much lithium chemicals production happens in China, that is a major force on spot pricing for lithium chemicals. But at the same time, it's not really a question of price as much as it's a question of units, right? How many lithium units do you have access to? We're really inspired by the fact that there's plenty of junior mining companies and companies that are about to become producing companies working on lithium mining and lithium chemicals production in the Western Hemisphere with whom we can do business. And so we're actively looking at partnerships to have as much of a localized and vertically integrated supply chain in North America as possible for those lithium chemicals. What we're doing now within our lab is using commercially relevant specifications from today's existing large-scale suppliers, the same suppliers which are used by your leading EV and cell maker brands, so that we integrate those specifications into our product from day one in the lab so that they can scale up to commercial production. Chirru, do you want to talk about iron phosphate precursor?
Yeah, sure. So our idea is even every experiment we do, even at an R&D scale, has to use commercially relevant grades of supplies that we get, right? So even our 10-gram tiny thermogravimetric analyzer batches use raw materials from some of the biggest Asian suppliers, for example. So for iron phosphate, we are actively exploring. So the synthesis routes for LFP are very well known, thanks to the LFP plus C consortium of patents. And our approach to iron phosphate is right now to be able to source it from the known manufacturers in China, but fully well understanding that if we were to have a domestic supply chain to be set up in the US, we need to think about a lot of the upstream setups as well. So how does the phosphoric acid supply chain play into being able to generate iron phosphate? Where are we going to assemble iron sulfate from? And this process often is energy intensive as well. So how do we basically station this very close to reliable source of power, right? So these are all the calculus that we are putting in place right now to be able to have precursor production as well that we will eventually own in-house.
Now, do you need to get patent licenses?
IP will be a principal source of value for a company like us for a long time, right? Licensing IP also comes at a little bit of a cost, in the sense that then it constrains us to work with certain style of partners. But it could be definitely a source of revenue generation for the company. How do we navigate the IP around right now? Our strategy is fairly straightforward, which is the chemistry space, the process space has been mercilessly explored as far as LFP goes, right? Some of the key IPs are expiring this year, but our idea is that once we have a product that we recognize in-house as a superior product to what exists in the chemistry, it has to be a proof of concept of either a superior process, which is tomorrow's process making the LFP that exists today better, or fundamentally a new chemistry that's improved upon what LFP does, right? And both of those would fundamentally qualify as innovation pieces beyond what exists in the IP landscape today.
Chirru is making a few key points here. The first is that the patents that govern LFP expire this year, and there's, around a dozen of them, probably maybe even a couple of dozen. But there's also been other patents that have come along over the years to improve on the core technology of LFP, and those patents are going to be in force for a number of years to come, which brings us to point 2, which is that if Mitra Chem works with a company that licenses those improvements to LFP, they're going to have to work around those patents. This brings us to point number 3. Mitra Chem is also developing their own improvements to the core LFP technology, so they may be able to completely sidestep any of the existing patents.
I'm going to jump back to something that Vivas said before, because I know you have to go here in a few minutes.
Yep.
Cost versus units. So the fact that you're focusing more on units than cost, does that mean that the cost of lithium iron phosphate and batteries in general is low enough now that people in the market who want those batteries are willing to pay whatever the premium is because they're able to make a profit off of them?
Well, we've already seen this happening. Right now, the race for securing lithium supply is completely about getting your hands on as many units of lithium carbonate or lithium hydroxide chemical as possible. And all of the contracts, the major contracts, have variable pricing components that are tied to market pricing. One of the reasons why we're seeing so much volatility in lithium pricing today is because after years of being lectured to about the imminent shortages in lithium chemicals, cathode makers, cell makers, automakers are lining up their lithium supply for the next 10 years. And it's a large number of hands reaching into a very small pot. What we need is more chemical supply to come online from the existing producers, and we need new producers. So once again, those junior mining companies and upcoming producers to bring their mining projects to market to produce lithium units that can be converted into the type of specialty chemical needed for cathode manufacturing, which then propagates all the way down the supply chain into the vehicles and energy storage solutions.
I'm curious about the actual process, about how you actually produce these LFP battery materials and how different that is from conventional processes, if you've made a lot of tweaks there, and also the environmental impact of the cathode material that you're producing in the United States versus like LFP material that might be produced in China?
What we are trying to do is use processes that are already established very well today, and then make process tweaks using trusted parameters in the process space and also chemistry space as well, right? So for the environmental impact, that's really important one. And because we are starting this company from ground up, we have the ability also to experiment with choices of incoming feedstock, which would allow us to reduce for example, the wastewater footprint that typically goes hand in hand with any wet processing that you have to do for making the cathode precursors, for example. So our intent is to be able to rely on the supply chains that we have domestically and be able to innovate on processes which would give us both a lower utility cost, but also environmental footprint as well.
All right. So do you expect the materials, now we're getting into the more economic side of things, do you expect the material that you're going to produce is going to be cheaper than the material that comes from overseas? Because, you know, there's tariffs, there's shipping costs, et cetera, or is it going to be relatively same price, or how does that differ from like a Chinese product?
Our goal is to make cathodes which would enable mass market electrification. By definition, cost has to be top of our minds. So what we're aspiring to do is to not let cost increase for a commensurate improvement in performance. That's the simplest answer here. Of course, there's going to be, depending upon what grade of LFP we make, that could be small differentiated cost, but we cannot simply justify a massive increase in cost to affect a performance improvement in LFP, because then the other strategy would be to make NMC-based chemistries cheaper, right? So cost has to be paramount.
Now, you also mentioned...
And that's the path to the $25,000 car right there, right? Is keeping your cost in your iron-based chemistry at the similar level that it is today, while focusing on improving GED, VED, and temperature handling, all these other characteristics that are needed.
Now, GED and VED, for people who are watching, I'm assuming you're referring to gravimetric energy density and volumetric energy density.
Yeah,
correct.
All right, I just have one more question for you. You guys have been hinting to gravimetric and volumetric energy density improvements. So what sort of improvements are you referring to? Like, how much of an improvement are you expecting?
At the cathode level, right? If we could affect even a 15% increase in the gravimetric energy density, 15 to 20%, at a cell level, and even beyond to a pack level, this would translate to roughly about 7 to 10% improvement in the energy density, right? This is, while this might seem like a small number, this, when paired with something like cell to pack, is a huge performance improvement at the same cost for LFP, right? So if you compare at the pack level, the difference between LFP and NMC, NMC 622 at least, the difference is on the order of like 4%, 4 to 5%. So if we can push the needle past the 10% improvement at a pack level, then that would be phenomenal for LFP. And this is the target that we're setting ourselves for initially.
And can you share any insights as to how you do that? Are you going to do that with the capacity, or are you going to do it with voltage, or like tap density, for instance?
But all of the above.
Okay.
All of the above. So, I mean, simply put, we can't go past LFP's density, LFP's current limitations without changing fundamentally something about iron, right? So there's going to be some chemistry changes involved, and ultimately process changes which would allow us to achieve better tap density. Today's LFP is about 1.4 gram per cc. So anything less than that is inconsequential from a scale-up manufacturer's perspective. So I think improving the tap density, coatings, and chemistry are the ways to go.
Okay, and for those watching, tap density is when you take some powder and you literally tap it, and you find out what the density is after you tap it. It's pretty straightforward, which I need to do a video on that. But I'm just going to summarize here because I know you have to go. But from what I'd gathered from this conversation is you guys are trying to move some of the supply chain from China and localizing it in the US, which has a number of benefits. And you're going to do that by increasing the rate that you can test these materials and bring them to market. Is there anything that you'd like? Oh, you're also going to improve, or you're attempting to improve the energy density and keep the cost competitive, or improve the cost. So is there anything you'd like to add to that, or is that pretty much it in a nutshell?
That's the gist. We are, focused on building iron-rich cathodes domestically in the United States, and we want to do it fast and at a lower cost.
All right. Well, this is exciting. Thanks for your time. I wish you guys all the best of luck, and thanks for taking the time today.
Jordan, it was truly an honor to be part of this show. Thank you so much for doing this interview for us. Appreciate it. And as Vivas mentioned, Mitra Chem is, we're putting a dream team together. As a founder, the people are everything to the company, and we are trying to assemble very talented material scientists, cell engineers, software engineers, and process engineers to be able to help us realize our dream of bringing iron-rich cathodes to market. So if you're interested in a career with this, please reach out to me or Vivas.
So thank you, everybody, very much for listening. If you'd like to learn more about our work, you can find out more at www.mitrachem.com. If you'd like to join our team, click on the careers section of our website. We welcome anybody with any level of experience, even if you're a total battery newbie. All you have to do is be motivated about solving climate change and about working on interesting problems in batteries here with our wonderful team in our lab in Mountain View, California. Jordan, thank you very much for having us here. You do a tremendous service to the battery community worldwide by running this channel. I've been a fan for a very long time, and it was a huge delight for me. It made my whole month that you invited me to come onto the show. Thank you.
Thank you for coming on. I've been following you for a while as well.
We will definitely do this again, hopefully in person in our lab when you can come out to California and visit us. All right?
All right. That sounds good.